This is the third type of projectile motion. And in this type of motion, we're going to basically combine the previous two types. So our object is going to start off some distance above the ground. In this case, let's say the distance is 6 meters. And it's going to be projected upwards. Again, let's give it an initial velocity of 10 meters per second. And it's traveling upwards at 53 degrees above the horizontal. Okay? So it has both an x component and a y component to its velocity. So it travels up, eventually coming to zero vertical motion, and then changes direction and comes down. Okay? So again, we still have uniform motion in the x direction, accelerated motion in the y direction. And again, typical question, what is this horizontal range? So let me clear the screen and make our diagram just a little bit smaller so we have some space. And let's start off again. So at 10 meters per second at 53 degrees, we can calculate both the x and the y component of the velocity. So it's going to be v times cosine theta is the x component. So it's traveling at 10 meters per second at 53 degrees. So 10 times cosine of 53 gives me a horizontal velocity of 6 meters per second. And in the y direction, because that's the opposite side of the triangle, we use sine theta. So 10 times sine of 53, and that works out to be 8 meters per second. Same that we velocities that we had in the last video. So we know the x and the y components, and what we're trying to find is the time. And unfortunately, in the vertical direction, there's no part of this equation that is zero, unlike the previous two types of projectile motion. In the first type, the initial y velocity was 0. In the second type, the displacement was 0. Both of those quantities are not 0 in this case, right? There's obviously an initial y component, and the vertical displacement, like we said, is the 6 meters that it travels downwards. So this equation has to be solved as if it was a quadratic equation. That means using the quadratic formula. So first let's write out what we have. So the vertical displacement, dy, is negative 6 meters. And the initial y velocity is the 8 meters per second times t plus 1/2 times the acceleration. Again, that's gravity. And times t squared. And for a quadratic formula, what we want to do is rearrange this so that it's set equal to 0. So I'm going to bring these two terms to the other side. And 1/2 of 9.8, that's 4.9. So 4.9 times t squared minus 8 times t minus 6 equals 0. Okay, so I've just rearranged this line and set it equal to 0. Now it's in the form of a quadratic equation. And in a quadratic equation, you have an a term, so that's this here is your a, and a b, which is this, and a c, which is this. And the quadratic formula is minus b plus or minus the square root of b squared minus 4ac, and all of that divided by 2a. So our value for the time is going to be equal to this. And you'll notice that by doing both plus this term and minus this term, I'm going to get two answers here. So two values for the time. Some of you might have calculators that actually have this formula programmed into them, some of the fancier graphing calculators. Otherwise, you're actually going to have to plug in the terms. It's not that difficult because the b minus b will be 8. Plus or minus the square root, b squared is 64, and then a is 4.9, and c is -6. It's important to include the positives and negatives on these terms, otherwise you're not going to get the right answer. And then we're going to divide by 2a, and because a is 4.9, 2 times that is always going to be 9.8, right? Because we got half of a, and then we make 2 times a again. So plugging this into your calculator, you're going to get 2 answers. The first answer being 2.19 seconds, and the second one being a negative 0.55 seconds. Obviously, time can't be negative, so I'm going to discount that one and say that it takes 2.19 seconds to make this whole trip. So I've determined the time, and just like before, what I was interested in finding was the horizontal displacement. So now I can take Vx, which was 6 meters per second, multiply that by my time, which I've just calculated, 2.19 seconds, and I end up with a horizontal displacement of 13 meters. So it travels 13 meters away from the base of the cliff. That's this distance here, from here all the way out to here, dx. Okay, so similar to before, the only difference, this equation is not very easy to solve. I have to use a quadratic formula to solve it. Or the quadratic equation, sorry. All right, let's move on. Same thing as before, we might be interested in finding the final y velocity, the impact velocity that it makes when it hits the ground. Again, there's going to be 2 components. We already know the x component, right? We calculated it before. Vx is the 6 meters per second in the horizontal direction. What I want to know is the final y component. And again, I need to know what is that final y component, sorry, not squared, after it's accelerated for a time. So Vy is going to be the initial y, which was 8, plus it accelerates due to gravity for this time 2.19 seconds. So the final y component here is negative 13.5 meters per second. So that is my final y component. And just like before, when I'm trying to find this velocity vector here, I take the square root of Vx squared and Vy squared. So my x component is still 6, and my y component is the negative 13.5. And that leaves me with a final y of 14.7 meters per second. And the direction, again, this angle here below the horizontal, is going to be the opposite side, which is the y component, divided by the adjacent side. When I take the inverse tangent of that, I end up with 66 degrees. So V is going to be 14.7 meters per second at 66 degrees below the horizontal. And that's how you solve the third type of projectile motion.